Let's go through the last problem set of high school physics for many of you.
Yay. I mean,
Don't we have another chapter? I thought we were doing another one.
No, I have a project in mind, although,
Goldberg.
although with only 3 weeks left, that's going to be a really tight squeeze. So, and one of those weeks is finals.
We should just do it all as one group.
That would be fun.
Yeah.
That would be fun. I think that would be cool. Maybe we could do it all together as one big class group.
That'd be quicker too.
I was really wanting to do that, but I didn't know how we could accomplish it. So that would be a neat way.
This group would be charged of that. That group would charge of that.
We don't have one really.
Well, you know,
There's was
the skeleton of it.
there's and they would admit to this is moderately terrible.
Yeah, they said
It
so.
was unsuccessed. There were some good
They
ideas.
were telling me we couldn't do it because those are the top people and they couldn't get it done.
In a similar amount of time, right?
Yeah.
So, and that's Sam brought that up to say that's a valid
Yeah,
point.
we were
So,
talking about that.
but let's talk about that next week. This week we still have plenty. So, chapter 22. Let's talk about conceptual questions. Indeed. Number 4 asks, a magnetic field is necessary if there is to be a magnetic flux passing through a coil of wire. That means a change in the magnetic field flux. Yet, of course you knew that because it's in the reading. Yet, just because there is a magnetic field does not mean that a magnetic flux will pass through a coil. Account for this observation. Ooh, how could there be a magnetic field without a magnetic flux?
So there could be a angle between the magnetic field and the surface. It's 90 or 270 because the cosine at that is 0. So then
I like your reasoning, but I don't know where the cosine comes in.
because in the equation it's cos. I don't remember.
The equation is like flux
It's-
equals
B times
BA cosine
BA
of
cosine theta.
Oh, for that part. Gotcha. Yes. Okay. Yes, that's a very good answer. I was thinking of it a little bit differently, but you're absolutely right. So, yes. But that would mean, okay, but it's, so what do you mean, what orientation would that be? So that is between the kind of an area vector and the flux. So if you have, say, a magnetic field here.
That's invisible.
Quiet, you.
Why are you writing with
You know you're making strange noises, right?
Yeah, and everybody on the video can hear that.
It's debatable because the video is hard to hear. It's easier to hear me usually, although with my phone recording, you might have a good angle for the mic. I don't know. So here is our wire in red, a magnetic field in blue. So what were you saying? You're saying when the angle is 90 or 270. What does that mean in a situation like this? What angle what are we measuring the angle between though?
Magnetic field and
Not quite.
Between the magnetic field and the area.
And the area, right? You'd said that was B times A times cosine of theta. And it's not just a BA, it's not just a BA formula, it actually means something. These two would be vectors. It's a dot product, right? So this would be B dot A. And by the way, I spoke with Ms. Case and she agreed that yes, of course, this is always going to work. But as I told you, that's not the point of it in math
You mean like
class.
FD cosine theta?
Yeah.
That always is-
It always works. And that's why I said, but that's not how she wants you to do it in math.
But that's not fair.
I did that way on my test and got it right, so.
Oh, yeah, I know. That's because it always works. But she wants you to do that way. Yes, Matt?
So area is a vector?
Area can be a vector. What direction is the area? So if this one,
Randomly pointed
it's
distance.
not a plane, it's a vector,
So it's like.
not a randomly pointed. It's kind of like a right-hand rule. So if we have
Twice?
Look at that.
current going like this,
It's counterclockwise.
it's out.
What's out? What?
Okay,
So here is what you're saying. You can't have a flux if this area vector, which is perpendicular to the plane of the loop, is itself perpendicular to the field. That would mean this loop, like this, we could have flux. Like this, where the area vector would be pointing up or down, that's at 90 degrees to the magnetic field, and the cosine of 90 is 0. So if this were angled like so in this magnetic field, we could not have a flux. Yep.
So it's not the way that it's, like, it wouldn't be, so right now the magnetic field is going
Into the board.
so it's going this way.
Yep.
and it's the way that the area is pointing, really.
So the area here is, the vector of area, this area, is perpendicular to the plane that the loop is in. The plane that the loop is in is here. What's perpendicular to the board? In or out. So in this case, the theta would be either 0 or 100. I'm not worried if you know that formula at all. We're not going to calculate on that. This is just a concept that I want you to get. If the magnetic field has an angle with this, you can have some flux. You were right in your description. But if you took this and rotated it so it was a plane like this, the loop was in a plane like this magnetic field could not cause any current in it. Flux is a change, and that would not mean a change in this field. You don't like that area could be a vector.
I just don't understand because you said that, so right now the area is like this and
The vector would
the
be
vector's
in or out,
yeah, but then once you rotate it like this, aren't they like same?
up or down, right? If I rotate this loop, I can't do that on the board. If this is the loop, and the loop is in this plane right now. Are you with me so far?
Yes,
And I rotate it.
so it's like this.
Yep. So here is the vector.
So you're rotating the magnetic field.
I'm rotating just the loop, not the magnetic field, just the loop. That's not helpful. So the loop has its own vector that's pointing either in or out, but now I rotate it, and so the vector is either pointing up or down. This angle is up. What's the angle between the area vector and the magnetic field? 90 degrees, because this is up and that one's in. What's the cosine of 90? So what's the flux? 0. That's what you were saying, Carissa.
Yeah, but before when you said that, so the plane is pointing, it's where the area is pointing out, like, it's in this, but then the area vector is going like this. It's not like this.
No, the
Correct.
magnitude.
Okay, because before you're saying it's just right here, and then you're saying the magnitude's like this. I thought that was perpendicular, but it's not. It's the same way.
Okay.
So I get it now.
Okay, good.
Pretty good.
Yes, Matt.
How can area be a vector?
Don't worry about it.
Just accept it.
Okay, so how else could you have a field and a coil here? We noticed, so one way is if this coil were rotated so that its area was in the same plane as the magnetic field, that would have 0 flux. That was the long and short of it. How else could this have 0 flux?
I have a question.
Nope, I asked first. Yes. What's that?
If you change the magnetic field, go up and down.
If it went, well, okay, so that would be the same thing. Yes, we rotate part of this. But how else could we have this magnetic field in this loop without a current caused in the loop? What do we need in order to have a current to make a current in a loop?
Magnetic field.
Don't just need a magnetic field. If you put a magnet in a coil of wire, you need a changing magnetic field. So how else could this not be
there's constant.
like if it was a constant field. So those are two ways. Now, what's your question, Skylar?
I lost track of what the question was.
Okay.
Not-
It was, it says, how could this setup not result in a current?
Okay.
So two ways. You could have the coil so that its area vector is perpendicular to the magnetic field, which kind of means it lies along the magnetic field, or you could have it so that it's a constant magnetic field. Next one. A conducting rod is free to slide along a pair of conducting rails in a region where a uniform and constant magnetic field is directed into the plane of the paper, as the drawing illustrates. Initially, the rod is at rest. Describe the rod's motion after the switch is closed. So, same kind of thing. Except now we have a battery, switch, long wires, and then a movable rod. Weird thing. Okay. So we want to say how, if we throw this switch, we're going to have current going through this. If we have current in a magnetic field, we must also then have a force. If we close this switch, so we close it up, first question is, from the diagram, what direction is current going to flow? Down where? It's circular. Positive to negative. Which side's the positive?
Top side.
Top side is. Because that one looks like a minus sign. So the current flows here. This is the movable part, so the current, it's important that the current would flow there. So then what the question is, if that's carrying current, it's going to have a force, and it's movable, so it will. So what direction? So we use right-hand rule. FBI. So current is down, so that means I is down. What direction is B? Into the board. F is that way. So this would experience a force in that direction.
So would it actually start to possibly move?
It would move, yeah, it would roll away.
That's pretty cool.
Yeah.
Doesn't the pole have its own magnetic field?
The which?
The
Sure.
pole, like wouldn't it point like this way and this way and this way and that way? Like going around?
It'd be going around, yep.
Yeah, so why would it move?
Well, it's still going to experience a force. Yes, it's also creating a magnetic field around it, but it's experiencing a force. So other things would experience a force because of this magnetic field and the magnetic field from all the wires.
Oh, so it's got a greater force going away?
Much greater, yep. And likewise, it would actually have a force attracting it to this. We saw that in one of our right-hand rule things. But if you did the calculation, it would have to be a very weak field here to be counteracted by that. Mm-hmm.
So why is the current down?
Because current goes in a battery from positive to negative.
Doesn't it have to go around first?
Yep. So we'd go around here.
So you just do the ultimate where it goes?
It's only going down in this section.
Oh, look at the rod.
Yeah, this green part's the only part that's movable.
So,
So everything else would have a force, but it's sort of assumed that it's
so
fixed in
the only
place.
thing creating a full circuit is through the rod?
Right. So this is a conducting thing that could roll or slide or something. Explain how a bolt of lightning can produce a current in the circuit of an electrical appliance even when the lightning does not directly strike the appliance.
Just to change it, it's like a giant current
Mm-hmm.
moment, so it goes current, like a change in current, and there's a change in magnetic field.
Yep, and if you've got appliances that have circuits in them, what happens if they are in the middle of a changing magnetic field?
They'll change their current as well.
They'll get a current in as well. So you'll get an electricity spike because of that. It'll just make it move inside the electronics. 8, 9, and 12. 8. A solenoid is connected to an AC source. A copper ring is placed inside the solenoid, with a normal to the ring being parallel to the axis of the solenoid. The copper ring gets hot, but nothing touches it. Why? So picture one of the large solenoids and a copper ring inside it, and then you've got an alternating current source on the ring itself. Why would that copper get hot? So here's the solenoid. I'm going to connect that to an alternating current source. So it's going back and forth, and then we're going to put a ring in here made out of copper. Yep.
So copper is a conductor, and as the current goes around the solenoid, it produces a current, which since the copper is a conductor, it kind of feeds off the current, and it's called induction, I think.
Mm-hmm.
And that's how the current heats up.
So electrons are moving back and forth, which causes friction, or which causes heat.
Okay, so that's why. So I know from your description you knew what was going on. I don't think it was quite a complete description. So let me add a little bit to it. We have an alternating current in this coil. So what can you say? So that means the current's going back and forth in the coil. What's going to happen to the magnetic field inside the coil?
Constantly change.
It's going to be changing constantly, right? And its direction will be changing in everything. So the magnetic field will be going back and forth, changing its magnitude and direction depending on where the current is. And here's a loop of conductor inside. So if it's experiencing a changing magnetic field, it will create its own current to sort of fight that. And as you said, that current means electrons are going around and around in it, bumping into other atoms. It's resistance. So if you had a superconductor, it would not heat up.
So wait, the copper tries resisting changing magnetic field?
Right, so it makes its own magnetic field and because of that, its own induced current.
And that creates heat?
Current creates heat in conductors, yeah. The P equals I times V. 9. A robot is designed to move parallel to a cable hidden under the floor. The cable carries a steady direct current of I. A sensor mounted on the robot consists of a coil of wire. The coil is near the floor and parallel to it. As long as the robot, so what we're looking at is, if we are looking down at the floor, we'd have the wire in the floor, a coil in the robot close to it and parallel to the floor. As long as the robot moves parallel to the cable with the coil directly over it, no EMF, which means voltage, electromotive force, no voltage is induced in the coil since a magnetic flux through the coil does not change. But when the robot deviates from the path, an induced EMF appears in the coil. The EMF is sent to electronic circuits that bring the robot back to the path. Explain why an EMF would be induced in the sensor coil. Matt?
Because since it's there and it's moving away, it's creating a difference in the magnetic field, and it'll make its own magnetic field to sort of pull back together.
Bingo. This starts moving up or down, it's not going to sense the same magnetic field from this wire. And it could even tell then based on what direction it's seeing. So it would get a different direction of current in the coil, and that would depend on the direction in this wire. And it could even see, am I going too far left or too far right?
But it also creates the magnetic field from the wire?
Yep. But that's typically pretty weak.
Yeah.
It's not nearly as much, but yes.
See, does
Any
it-
moving current will have its own as well.
Goes like number 8, trying to resist.
Bingo. Yep. Number 12, last one. When a switch in the circuit in the drawing is closed, so this has got the loops, I'll show you an example of it. A current is established in the coil and the metal ring jumps upward. I've actually got Sam Vandaloo working on one for me. I tried. well, I'll use mine. Sam's is going to be, I'll show you Sam's too. Pretty grand when it's done. So he's going to take and very neatly wrap a whole bunch of wire around this. And then we can put an iron core in this in the center to make it a pretty powerful electromagnet. And the other end of this, very high tech, plugs in.
Is that the old Chelsea pole?
No, that's from an old electromagnet to pick up nails or something.
No, your pole you got like made.
Yeah, it's from like a VCR or something.
Well, I thought it was from one of the black, yeah.
No, it's not. No, it. So this is a jacket that would have been plugged into the box of something like a VCR. But I need to plug this in. Now it's a concern when we do that it could overheat. But that's something for another day. Ooh, we'll have to be careful with this. It's already big enough. So here's my ring. And if I plug this in, as it says here, and get enough current through it, the ring will jump off of this. I have enough to do that I didn't get this done this year, which is why I asked Sam to do it. But you can imagine what it would happen. So I push the button switch, and it jumps off. And it asks, why?
So there's a change in current which makes a magnetic field going this way. Is that little silver thing like a bunch of coils wrapped up as well?
Technically no, but sort of yes. It's a solid piece of aluminum.
So if it were like coils, then they'd be going around and it would be going this way and it would push down there. Since they would change in magnetism, it would also want to stay the same. So it would push away from the new magnetism that's pushing toward it.
Yes, I think so, but let's see if we can get a little clearer explanation.
Because when the magnetic field, when it's actually active, it creates the force, and the force is what pushes the aluminum.
Why does it create a force?
Because of the flux.
Yes?
So they have like the same magnetic like field and you know the same poles like
Repel? Mm-hmm.
So that's kind of what this is.
This is another application of that. So this is the Lenz's law thing. So let's pretend for a moment that the current is going around here at some moment. And so this way, so then the north pole created by this post would be pointing up, but it's alternating current, so its value would be changing. So it could be increasing or decreasing. So if this has a north pole facing up, as Matt was saying, that's going to induce a current in here, changing magnetic field. But also it changes it in such a way that the current in here makes its own magnetic field to oppose that. So a north pole down, and that would repel. As it's decreasing or putting the south pole up, so north pole down, going the other way around, opposite would happen. Now, this one would see the other change, and it would try and resist it, making its own south pole face down, but that's still repelling from the south pole that's in this coil. So the current will keep changing directions in this, just as it does because of the alternating current from the wall socket here. And that will create constantly opposing magnetic fields from the ring and the coil. Mm-hmm.
So an alternating current is just current that gets stronger and weaker. And
Right.
stronger.
So the voltage is actually a sine wave with half of its time above zero, half of its time below. So it's pushing and then pulling. And the amount is a wave. Mm-hmm.
So will it just go like up and down on the thing, or will it fly off?
It actually flies off. It'll if it's a good one, then it'll jump up to the ceiling.
So it still has a rail gun.
Kind of. A railgun works a bit differently because a railgun actually vaporizes part of the bullet, part of the projectile. A railgun arcs across, so it's got two high voltage prongs with a bullet in the center, and goes up. It arcs across to the bullet and then across, and that heats it up. Current again floating, and then it actually vaporizes that part of the bullet. Well, there's no place for it to go except up the barrel. So it's sort of like a gunpowder explosion that creates a whole bunch of gas that forces a projectile out, but it's using electricity to do it. Yeah.
So instead of sticking your rocket on it, it turns the bullet into the rocket.
More or less, yep. hmm
So the ring would go off of the thing, would it still have a magnetic field once it's like off that would want to suck?
Not very much once it's far enough away from this, because the magnetic field doesn't extend strongly away from this.
But if you get it right, will it go up and then down and then bounce back up?
It could, sure. Yep.
It'll be like a little bounce back.
Yep. So it'd shoot it up. Kinetic energy would leave, potential to fall back down. But in a contraption like this, you'd never be able to get it just going straight up. So you'd have to have some sort of, if you continued the pipe, maybe it would go up on the pipe and then slide back down and then up. But the thing is, this is called a momentary switch. It's only on when you're actually pushing it, and that's important because with the low resistance and 120 volts, all this wire will heat up very, very quickly. So that's why that definitely worked on my first version, the heating part. It just didn't shoot a ring. So I was on the right track, but I only had two layers of coils on that. Okay. Thus concludes our review part there.